What if everything you thought you knew about gravity was turned upside down, literally? Picture an object that doesn't fall toward the Earth but pushes away from it, defying the very force that keeps us grounded. This isn't science fiction, it's the mind-bending reality of negative mass, a theoretical concept that could shatter our understanding of physics and unlock possibilities straight out of a cosmic daydream. From anti-gravity propulsion to warp-speed space travel, the implications of negative mass are so extraordinary, they blur the line between imagination and science. And today, we're diving deep into 28 of its most shocking possibilities, each one more revolutionary than the last. Think about the last time you dropped something, a pen, a phone, a spoon, and watched it obey gravity's unbreakable rule. Now erase that instinct from your mind. In a universe with negative mass, objects wouldn't just resist gravity, they'd accelerate in the opposite direction, like a car speeding backward when you hit the gas. Scientists have toyed with this idea for decades, but recent breakthroughs suggest it might not be as far-fetched as we once believed. Imagine spacecraft hovering effortlessly above a planet's surface, or propulsion systems that require no fuel, just the bizarre, counterintuitive push of negative mass. The implications aren't just about defying gravity, they're about rewriting the rules of the cosmos itself. But here, where it gets even stranger. Negative mass doesn't just challenge gravity, it twists the fabric of spacetime, creating effects that sound like pure magic. Wormholes stable enough to traverse, energy sources that defy conservation laws, even time manipulation could all be on the table if this phenomenon exists. And while it's still theoretical, the mere possibility has physicists and engineers rethinking the future of technology. What if the key to interstellar travel has been hiding in the equations all along, waiting for us to grasp its potential? That's the journey we're embarking on today, one that will take you from the edge of known science to the frontiers of what might just be possible. So settle in, because by the end of this exploration, you'll never look at the universe the same way again. The first shocking implication of negative mass flips gravity's script entirely. Instead of pulling objects together, it could push them apart, creating a force that acts like true anti-gravity. Picture a spacecraft not straining against Earth's pull with roaring engines, but silently lifting off as if the planet itself were repelling it. This isn't just about floating, it's about acceleration without propulsion, a concept that upends centuries of physics. Traditional rockets guzzle fuel to fight gravity, but negative mass could render them obsolete, replacing fiery exhaust with a natural repulsion that propels us skyward effortlessly. The energy savings alone would be staggering, turning interplanetary travel from a fuel-bound slog into a graceful glide across the solar system. But the possibilities go far beyond mere hovercraft. Scientists speculate that negative mass might be the missing ingredient for warp drives, bending spacetime in ways that conventional matter can't. The equations hint at this. Negative mass could theoretically stretch spacetime behind a ship while compressing it ahead, creating a bubble that moves faster than light without breaking relativity. It sounds like fantasy, but the math suggests it's at least plausible. Even more intriguing, negative mass could stabilize wormholes, those cosmic shortcuts often dismissed as unstable quirks of theory. With repulsive gravity holding a wormhole's throat open, traversable tunnels across the universe might no longer be just a sci-fi dream. Yet the biggest hurdle isn't just proving negative mass exists, it's harnessing it. Hypothetical models suggest it would behave bizarrely, like accelerating toward you when pushed away, a paradox that makes engineering a nightmare. But if we could tame it, the rewards would redefine human potential. Cities floating above volcanic worlds, probes darting between stars without fuel, even time dilation becoming a navigable tool, all hinge on this one radical idea. The universe has never been bound by our expectations, and negative mass might be the next great reminder that the rules we take for granted are just waiting to be rewritten. Equations painted a universe far stranger than we ever imagined, one where spacetime could twist into tunnels connecting distant corners of reality. But there's always been a catch. Wormholes, those hypothetical cosmic shortcuts, should collapse instantly under their own gravity. That's where negative mass changes everything. Picture a mysterious substance with repulsive gravity propping open the walls of a wormhole like an invisible scaffold, defying the crush of normal physics. Suddenly, what was once a fleeting mathematical quirk becomes a stable highway through the cosmos. A trip from Earth to Alpha wouldn't take decades. It could take mere seconds, like stepping through a door. The real shock isn't just distance, though, it's time itself. Wormholes linked to negative mass could warp the flow of causality, creating paths where the exit exists before the entrance. That means you might arrive at your destination before you even left, plunging headfirst into the infamous grandfather paradox. What happens if you prevent your own birth? Physics has spent decades wrestling with these questions, but negative mass adds a startling twist. It might not just enable time travel, but make it controllable. Imagine adjusting the tension between positive and negative mass like a dial, fine-tuning a wormhole's timeline instead of tumbling helplessly through chaos. Yet the universe rarely gives us free lunches. Even if negative mass stabilizes wormholes, the energy required to create one could dwarf anything humanity has ever produced. Some theories suggest it would take compressing a star's worth of matter into a singularity, while others hint that exotic quantum materials might offer a. And then there's the unnerving possibility that wormholes themselves could be unpredictable, snapping shut or rerouting destinations like a cosmic game of roulette. But here, the tantalizing part. If nature already allows negative mass somewhere in the universe, perhaps in the quantum foam of empty space or the heart of distant galaxies, then these tunnels might not just be possible. They might already exist, hidden in the dark, waiting for us to find the key. The third shocking implication of negative mass isn't just revolutionary. It's downright heretical to the foundations of physics. Imagine a machine that never runs out of energy, humming along indefinitely without fuel, sunlight, or any input at all. That's the tantalizing possibility of negative mass enabling perpetual motion, a concept long dismissed as impossible under the ironclad laws of thermodynamics. Yet here's the twist. Negative mass particles wouldn't just resist gravity. They could defy energy conservation itself, creating systems where motion begets more motion in an endless, self-sustaining loop. Take a simple thought experiment. A negative mass object and a positive mass object placed near each other. Instead of attracting like normal matter, they chase one another in a runaway acceleration, the positive mass pushing forward while the negative mass accelerates backward, creating a feedback loop of endless motion. No friction, no decay, just pure, unrelenting energy. It's the kind of phenomenon that would make a steam engine blush, and it could rewrite the rules of how we power our world. Suddenly, the dream of clean, limitless energy isn't about harnessing the sun or splitting atoms. It's about tapping into the bizarre physics of repulsive gravity. But before you envision infinite energy powering your home, there's a catch. The second law of thermodynamics, the sacred decree that disorder always increases, stands firmly in the way. Or does it? Some theorists argue that negative mass might not so much break the laws of thermodynamics as bend them, creating localized pockets where energy flows in reverse. Think of it like a river that occasionally runs uphill, not because the riverbed changed, but because the water itself has a mind of its own. If true, this could unlock technologies like self-charging batteries or propulsion systems that refuel simply by existing in the right configuration. The implications are staggering. Spacecraft could cruise between stars without refueling, industrial machines might operate forever without maintenance, and entire cities could run on devices that never deplete. Yet the skeptics aren't wrong to raise an eyebrow. After all, perpetual motion has been the graveyard of countless overambitious inventions. The difference here is that negative mass isn't a clever trick or a loophole. It's a fundamental reimagining of how matter behaves. And if even a fraction of these theories hold water, the energy crisis of tomorrow might not be about scarcity, but about learning to control the of infinite possibility. Of course, the universe rarely hands us free lunches. Even if negative mass enables perpetual motion, harnessing it safely would be a nightmare. Runaway reactions could spiral out of control, and the fine line between limitless energy and catastrophic instability might prove razor-thin. But that's the thrill of frontier science. It doesn't just answer our questions. It forces us to ask ones we never thought possible. The universe isn't just expanding, it's accelerating. Galaxies fleeing from one another faster and faster, as if some invisible hand were stretching spacetime itself. Astronomers call this mysterious force dark energy, a placeholder for something we don't yet understand. But what if the answer lies in negative mass? Picture a cosmic repulsion woven into the fabric of reality, not pulling matter together like gravity, but pushing it apart with relentless force. This isn't just a wild guess. Some theories suggest dark energy could be the collective effect of negative mass particles scattered across the cosmos, acting like anti-gravity on a universal scale. Think of it like this: drop a single negative mass object into a room and it might levitate oddly. But sprinkle it evenly throughout the universe, and suddenly you have a repulsive force stretching space itself. That's the startling possibility. Dark energy might not be some exotic new field or quantum fluke, but the accumulated push of negative mass hiding in plain sight. It would elegantly solve one of cosmology's biggest puzzles: why the universe's expansion isn't slowing down from gravity's pull, but speeding up against all expectations. The implications go beyond mere explanation. If dark energy is negative mass in disguise, it could reshape our understanding of the universe's fate. Right now, astronomers debate whether expansion will lead to a cold, lonely big freeze or a violent big rip, where galaxies, stars, and even atoms are torn apart. But with negative mass in the equation, the future might hold stranger possibilities, like a universe that doesn't just expand, but does so in unpredictable bursts, or even reverses course if the balance between positive and negative mass shifts. Yet the most tantalizing clue lies in the numbers. Measurements of dark energy's strength align suspiciously well with theoretical predictions of how negative mass would behave on cosmic scales. It's as if the universe left us a breadcrumb trail, hinting that the answer to one of science's greatest mysteries has been lurking in its equations all along. Of course, proving it is another matter. Negative mass remains elusive, and dark energy could still be something entirely different. But the mere possibility ties together two of physics' most perplexing enigmas, suggesting that the key to understanding the cosmos might lie in the most counterintuitive idea of all: a gravity that pushes, not pulls. Black holes have long been the ultimate cosmic dead ends, gravity's inescapable prisons where not even light gets a parole hearing. But negative mass could shatter that reputation entirely, turning these celestial monsters into something far more mysterious: cosmic escape artists. Picture the event horizon, that infamous point of no return, suddenly sporting a hidden. If negative mass exists inside a black hole, its repulsive push might battle the crushing pull of normal gravity, creating unstable pockets where the usual rules break down. Information, energy, even matter itself could theoretically slip through cracks in the universe's most unforgiving vaults. This isn't just about breaking physics, it's about salvaging it. One of the biggest headaches in modern cosmology is the black hole information paradox, the unsettling idea that anything swallowed by a black hole vanishes from the universe forever, erasing the fundamental laws of quantum mechanics. But negative mass offers a radical solution. What if that information isn't destroyed, just rerouted? Like smoke seeping under a door, Particles carrying data might trickle back out, not through the black hole's main entrance, but through quantum backchannels propped open by negative mass's repulsive grip. The implications ripple outward. Black holes might not be the eternal tombs we thought, but more like cosmic transformers, devouring matter on one end and subtly leaking altered versions of it elsewhere. Some theories even suggest this could explain mysterious high-energy particles like cosmic rays, which appear to originate from nowhere with impossible vigor. Could these be the fingerprints of negative mass at work, ejecting trapped energy like a pressure valve? Yet the most mind-bending possibility isn't escape, it's communication. If negative mass allows black holes to emit signals, they might not be the silent monsters we imagine, but chatterboxes broadcasting their secrets into the void. Astronomers could one day tune into these distorted transmissions, decoding the physics of the singularity itself. Of course, the math is fiendishly complex, and the margin between theory and fantasy remains razor-thin. But if negative mass holds the key, black holes might just be the universe's most convoluted messengers, whispering answers to questions we're only beginning to ask. The catch, negative mass inside a black hole wouldn't play nice. Its chaotic push and pull could destabilize the singularity, triggering eruptions or even premature black hole decay. Imagine a stellar heavyweight champion suddenly stumbling mid-fight. The cosmic arena wouldn't know what hit it. Whether that's a feature or a bug depends on who you ask, but one thing's certain. In a universe with negative mass, even the darkest corners might not be as final as they seem. Warp drive has always been the ultimate cosmic cheat code, a theoretical loophole that could zip you across the galaxy without breaking speed limit. The catch? It needs something called exotic matter, a hypothetical substance with negative energy density to bend spacetime into a traveling bubble. Enter negative mass, the game changer that could finally make this sci-fi staple a reality. Imagine swapping out the universe's rarest hypothetical ingredient for one that's merely bizarre, turning a pipe dream into a plausible engineering challenge. The math is mind-bending yet elegant. A warp drive works by compressing spacetime in front of a ship while expanding it behind, effectively surfing a wave of distorted reality. Normally, this requires energy conditions so extreme they might not exist in nature. But negative mass flips the script. Its innate repulsive gravity could do the heavy lifting, stretching and squeezing spacetime like putty, without demanding impossible energy densities. Suddenly, the drive isn't just a chalkboard fantasy. It's a blueprint waiting for the right materials. NASA's lab has already tiptoed into this arena, testing rudimentary models that hint at how negative mass might manipulate spacetime on microscopic scales. Their experiments with quantum vacuum thrusters skirt the edge of known physics, suggesting that even a whisper of negative mass effects could revolutionize propulsion. Picture a spacecraft encased in a warp bubble, not burning fuel but riding the contours of spacetime itself. Silent, efficient, and faster than light without ever technically moving. Yet the real magic lies in relativity's fine print. A warp drive doesn't accelerate the ship. It moves the space around it, dodging the cosmic speed limit by technically keeping the vessel at rest. Negative mass could stabilize this bubble, preventing the catastrophic collapse or deadly radiation surges that plague theoretical designs. It's like building a tunnel through a mountain. You're not climbing over, you're going through, with negative mass as the support beams holding the walls apart. Of course, skeptics abound. The energy requirements, even with negative mass, could dwarf anything humanity can muster, and the control mechanisms would need precision beyond our wildest tech. But here's the kicker. If nature already permits negative mass somewhere in quantum fields, cosmic voids, or undiscovered particles, then warp drives might not be engineering problems. They'd be scavenger hunts, waiting for us to uncover the universe's hidden toolkit. And if that day comes, the stars wouldn't just be destinations. they'd be neighbors. The irony is delicious. For centuries, we've dreamed of sailing the cosmos on rockets and sails. But the real shortcut might lie in embracing the universe's strangest quirk, a gravity that pushes instead of pulls, turning spacetime into our highway. The drive isn't just about speed, it's about perspective. And negative mass might be the lens that finally brings it into focus. Time doesn't just pass, it bends, warped by gravity's invisible hand like a river flowing slower near a black hole's crushing depths. But what if that river could run backward? Negative mass doesn't just tweak the rules of gravity, it inverts them, and that includes time itself. Showed us that massive objects slow time, clocks tick slower on Earth's surface than in orbit. Now flip the script. Negative mass could theoretically speed time up, creating pockets where seconds race ahead like minutes, or even stranger, where cause and effect start unraveling in reverse. Picture a chamber lined with negative mass, a room where time accelerates instead of dragging. Step inside and you might watch a candle burn to its base in seconds while the outside world barely moves. The implications aren't just about speed, they're about direction. If negative mass can make time flow faster, could it also twist the arrow of time backward? The math hints at yes, though the universe tends to fight such paradoxes tooth and nail. Imagine a device that doesn't just pause or fast-forward reality, but rewinds it, turning shattered glass back into a whole cup. It's the kind of power that would make even the most daring physicists hesitate. Yet the real shock isn't the mechanics, it's the consequences. Time dilation reversal wouldn't just challenge physics, it would upend ethics, law, even our grasp of reality. What happens to accountability if crimes can be undone before they occur? How do you govern a world where someone could retroactively erase mistakes or successes? The grandfather paradox isn't just a thought experiment anymore, it's a potential user manual. And then there's the cosmic irony. If negative mass lets us rewind time locally, would the rest of the universe even notice? Or would we just carve out tiny islands of altered history in an indifferent cosmos? The practical hurdles are just as dizzying. Stabilizing a negative mass time field would require precision beyond anything we've engineered. One miscalculation, and you might age a decade in an hour or trap yourself in a loop where Tuesday repeats indefinitely. Even scarier, negative mass might not just bend time, it could fracture causality, creating scenarios where an effect precedes its cause, like an echo arriving before the shout. Some theories suggest these paradoxes would self-correct, the universe snapping back into order like an overstretched rubber band. Others warn of branching timelines or irreversible rips in the fabric of reality. But here's the twist, nature might already be doing this. Quantum fluctuations and dark energies accelerating expansion hint that spacetime isn't as rigid as we thought. If negative mass exists in the wild, lurking in cosmic voids or entangled in quantum fields, then time manipulation might not be a human invention but a natural phenomenon we're just beginning to recognize. The universe has never been a passive stage, it's an active participant, full of tricks we're only starting to glimpse. And if negative mass is one of those tricks, then time itself might be far more flexible than we ever dreamed. The question isn't just whether we can harness it, it's whether we should. Time dilation reversal isn't a tool, it's a responsibility, a genie that once let out of the bottle might not go back in. Yet that's the thrill of science at the edge. It doesn't just reveal what's possible. It forces us to ask who we become when the impossible is suddenly within reach. Imagine walking down the street and seeing an entire train gliding silently above its tracks. Not a single wheel touching metal, just pure, effortless levitation. This isn't magic, it's the startling promise of quantum levitation supercharged by negative mass. We've already glimpsed hints of this phenomenon with superconductors, those mind-bending materials that lock themselves in midair when chilled to extreme temperatures, defying gravity through quantum locking. But introduce negative mass into the equation, and suddenly the effect isn't just a lab curiosity, it's a world-changing technology. Think of it like upgrading from a flickering candle to a blazing spotlight. Superconductors hover because they expel magnetic fields, creating a fragile balance between upward push and downward pull. Negative mass could tip those scales dramatically, generating a repulsive force so strong it wouldn't just suspend objects, it could launch them skyward with zero energy input. Picture highways where cars float inches above the ground, eliminating friction entirely, or construction sites where entire buildings are assembled midair, their supports replaced by invisible fields of anti-gravity. The energy savings alone would be staggering, turning everything from transportation to urban planning into a frictionless dream. Then there's the everyday revolution, anti-gravity shoes. It sounds like something from a cartoon, but the physics checks out. A thin layer of negative mass material in your soles could counteract Earth's pull, letting you walk with moon-like buoyancy or even take leaps that defy human limits. Athletes could shatter records, rescue workers could navigate collapsed buildings with eerie grace, and the very idea of heavy lifting might vanish from our vocabulary. But the real game changer, infrastructure. Bridges that never sag, power lines that never droop, even floating cities perched above flood zones or volcanic terrain, all possible if negative mass amplifies quantum locking to macroscopic scales. Imagine Tokyo or New York built on platforms suspended by repulsive gravity, untethered from the Earth's instability. The materials wouldn't just hover, they'd self-stabilize, adjusting to loads automatically like a cosmic trampoline pushing back against every step. Of course, the hurdles are as towering as the possibilities. Negative mass remains theoretical, and scaling quantum effects to everyday objects would require breakthroughs we can barely envision. Yet the tantalizing part is this: nature might already be showing us the way. From the eerie precision of superconducting levitation to the way dark energy seems to push galaxies apart, the universe whispers hints that anti-gravity isn't just possible, it might be hiding in plain sight. The question isn't whether we'll harness it, but how soon we'll recognize the tools we've been overlooking all along. And here's the kicker: unlike rockets or batteries, quantum levitation with negative mass wouldn't just improve existing tech, it would rewrite the rules of movement itself. No fuel, no emissions, just silent defiance of gravity's oldest tyranny. The future of transportation might not roar with engines. It might float, utterly silent, on the edge of the impossible. Stars have always been the universe's furnaces, gigantic balls of plasma where gravity crushes atoms together until they ignite. But what if there's another kind of star, one where gravity doesn't pull inward but pushes outward? That's the mind-warping possibility of negative mass stars, celestial oddities that wouldn't just defy physics, they'd rewrite the cosmic rulebook. Imagine a star that doesn't shine from nuclear fusion, but from some bizarre anti-gravitational energy, its light curving away instead of bending toward it like a cosmic lighthouse running in reverse. These wouldn't be stars as we know them. They'd be something closer to cosmic mirages. Normal stars warp space-time, creating the gravitational lenses astronomers use to peek at distant galaxies. A negative mass star would do the opposite, bending light outward in strange, halo-like patterns that could make objects behind it appear to shrink rather than magnify. Telescopes might spot these anomalies as voids where light behaves unnaturally, like a patch of sky that refuses to play by the rules. And their structure, forget dense cores. These stars could have hollow centers, their negative mass particles repelling each other so fiercely they create a stable, self-sustaining shell of anti-gravity. Then there's the radiation. Ordinary stars emit light because their crushing gravity generates heat, but a negative mass star might glow for the opposite reason. Its repulsive gravity could theoretically convert space-time distortions directly into energy, producing a cold, eerie light unlike any in nature. Some models suggest they'd pulse unpredictably, dimming and brightening as their unstable gravity fields oscillate. If they exist, astronomers might have already seen them and dismissed them as instrument glitches or unexplained dark spots in the cosmos. The real puzzle is how they'd form. Normal stars coalesce from gas clouds collapsing under gravity, but negative mass would resist that pull, meaning these anti-stars might require an entirely new birth process, perhaps emerging from quantum fluctuations in the early universe or condensing in regions where dark energy dominates. There could be equally strange. Instead of burning out or exploding, a negative mass star might simply unravel, its repulsive particles flinging themselves apart in a silent, invisible dissolution. Yet the most tantalizing idea isn't their existence, it's their potential as cosmic signposts. If we ever spot one, it wouldn't just confirm negative mass, it'd reveal an entire shadow universe of physics operating in parallel to our own. These wouldn't be stars, they'd be messages from a stranger, wilder cosmos, one where up is down, push is pull, and the rules we've always known are just the beginning. Right now, the universe seems eternal, galaxies drifting, stars burning, the cosmic dance playing out on a timescale so vast it dwarfs human imagination. But what if the grand finale isn't a slow fade to black, but a violent, explosive end where reality itself is torn apart at the seams? That's the terrifying premise of the Big Rip, a doomsday scenario where dark energy, potentially fueled by negative mass, becomes so dominant it doesn't just push galaxies apart, it shreds them atom by atom. Picture this: first, galaxy clusters are ripped apart, their gravitational bonds no match for the accelerating expansion. Then, individual galaxies unravel, stars flung into the void like sparks from a bonfire. Next, solar systems are torn asunder, planets ripped from their orbits. But the horror doesn't stop there. Eventually, the repulsive force grows so strong it overpowers the very glue holding matter together. First planets, then rocks, then molecules, and finally atoms themselves, splitting protons and electrons apart in a final, apocalyptic instant. The universe wouldn't just end. It would dissolve into a sea of disconnected particles, each racing away from the others faster than light, leaving nothing but cold, empty silence. The chilling part, the math suggests this isn't just speculation. If dark energy's strength increases over time, and if it's linked to negative mass, the Big Rip isn't just possible, it's inevitable. Current estimates place this event roughly 100 billion years in the future, but the timeline could shift if negative mass behaves unpredictably. Some models even suggest pockets of the universe might rip apart sooner, creating bizarre islands of stability in a disintegrating cosmos. Yet here's the twist: negative mass might not just be the destroyer, it could also be the universe's reset button. A handful of radical theories propose that the Big Rip wouldn't be the end, but a rebirth. As spacetime is torn apart, the incredible energy released might trigger a new Big Bang, birthing an entirely new universe from the ashes of the old. In this scenario, negative mass isn't just a cosmic wrecking ball. It's the catalyst for an endless cycle of creation and destruction, where every end is just a prelude to another beginning. The irony is profound. The same force that could one day annihilate everything might also be the key to eternity. Whether the Big Rip is a final curtain or an intermission in the universe's grand play depends entirely on the quirks of negative mass, a substance we've yet to prove exists. But that's the thrill of cosmology. It forces us to confront not just the limits of our knowledge, but the limits of reality itself. The universe has never been gentle, and if negative mass is its hidden architect, the future might be far stranger and far more violent than we ever dared to dream. For now, the Big Rip remains a specter on the horizon, a reminder that the cosmos operates on scales and rules we're only beginning to grasp. But it also underscores a deeper truth. The universe isn't static. It's a living, evolving entity, capable of both breathtaking beauty and unimaginable destruction. And if negative mass is part of that story, we're just starting to read the first page. Quantum entanglement already defies common sense. Particles separated by light years can mirror each other's states instantly, as if space-time doesn't exist between them. Famously called it spooky action at a distance, but negative mass could crank that spookiness up to cosmic levels. Imagine entangled particles not just communicating faster than light, but leveraging repulsive gravity to push and pull each other across vast distances, creating a network of influence that could rewrite the rules of energy and information transfer. This isn't just about particles twinning their spins, it's about harnessing entanglement as a practical tool. Normally, entanglement is fragile, collapsing at the slightest interference. But negative mass might stabilize it, acting like a protective buffer against decoherence. Picture a quantum internet where signals aren't sent through cables or satellites, but broadcast instantaneously through entangled negative mass particles, immune to lag or interception. Secure communications, real-time data streaming across interstellar distances, even distributed energy grids that draw power from entangled sources light years away, all become tantalizing possibilities. The real breakthrough, though, lies in energy teleportation. Quantum physics already allows for virtual energy borrowing across tiny gaps. Negative mass could scale this effect dramatically, enabling entangled systems to share not just information, but actual kinetic energy. Think of two spacecraft linked by entangled negative mass particles. Pushing one forward could simultaneously pull the other backward, creating propulsion without fuel or exhaust. It's like a cosmic Newton's cradle, where every action has an equal and opposite reaction, instantly across any distance. Yet the universe rarely gives us free lunches. Amplified entanglement might come with bizarre side effects, like feedback loops where energy transfer spirals out of control or causality violations where effects precede causes. Some models suggest negative mass entanglement could puncture spacetime itself, creating microscopic wormholes between linked particles. Others warn it might destabilize the quantum vacuum, triggering unpredictable energy eruptions. The most profound implication: this could be nature's cheat code, a hidden layer of physics where distance is an illusion and energy is fungible. If negative mass entanglement exists, even in some corner of the cosmos, it would mean the universe is far more interconnected than we ever imagined. Not just through gravity or light, but through invisible threads of influence weaving reality together at the most fundamental level. And if we learn to tug on those threads, the technological revolution wouldn't just be groundbreaking, it'd be galactic. Imagine stepping onto a balcony not anchored to solid ground, but suspended high in the swirling clouds of Jupiter. A floating metropolis drifting effortlessly through the gas giant's turbulent skies, held aloft not by engines or balloons, but by the sheer repulsive force of negative mass. This isn't the distant dream of sci-fi. It's the startlingly plausible future of anti-gravity cities, where entire habitats could hover in atmospheres or deep space without the crushing weight of traditional support structures. The key lies in negative mass's ability to invert gravity's pull, turning the most hostile environments into potential homes. Take Venus as a test case. Its surface is a hellscape, temperatures hot enough to melt lead, pressures like an ocean's depths, and skies choked with sulfuric acid. But 50 kilometers above, the atmosphere is eerily Earth-like, with similar pressure and even breathable air if you could separate the nitrogen and oxygen. Floating cities here wouldn't need massive helium envelopes or constant propulsion adjustments. A lattice of negative mass material could provide stable, permanent buoyancy, anchoring habitats in the Venusian sky like islands in a toxic sea. Scientists have toyed with cloud cities for decades, but negative mass removes the biggest hurdle, the staggering energy cost of staying aloft. The real game changer, though, is scalability. Unlike balloons or wings, which grow impractical at larger sizes, negative mass's repulsive effect scales with volume. A small platform might hover modestly, but a city-sized structure could float with the same ease, its anti-gravity field distributing the load evenly. Picture vast agricultural domes drifting in Jupiter's upper atmosphere, harvesting hydrogen for fuel while storms rage harmlessly below. Or orbital colonies that don't require spin gravity. Their negative mass cores could simulate Earth's pull artificially, letting residents walk normally in deep space. The architectural freedom is dizzying. Buildings could dangle like inverted skyscrapers from floating foundations, their weight offset by the repulsion beneath. But the most radical possibility isn't just floating, it's moving. A negative mass city wouldn't be tied to one location. With careful manipulation of anti-gravity fields, entire metropolises could migrate with the seasons or follow resource-rich atmospheric currents. Gas giants like Uranus, once written off as inaccessible, might become nomadic homelands, their floating settlements surfing the jet streams for. Even Earth could see neighborhoods rising above flood zones or volcanic regions, untethered from the planet's vulnerabilities. Yet the challenges are as vast as the opportunities. Stabilizing such cities would require precision engineering to prevent runaway acceleration. Imagine a Manhattan-sized island suddenly lurching skyward like an untethered helium balloon. And then there's the psychological toll. Humans evolved with solid ground underfoot, and the constant vertigo of a floating world might demand new forms of architecture to trick our instincts. But if history teaches us anything, it's that humanity adapts, especially when the alternative is limitless living space among the clouds. The irony is poetic. For centuries, we've dreamed of conquering other worlds by replicating Earth's conditions. But negative mass suggests a wilder path, not changing alien environments to suit us, but redefining what it means to inhabit them. The future of colonization might not be about planting flags in rock, but sailing the cosmic winds in cities that defy gravity itself. What if the multiverse isn't just a collection of disconnected realities, but a vast network of worlds linked by invisible tunnels? Tunnels held open by the repulsive force of negative mass. The idea of parallel dimensions has long been a staple of sci-fi, but modern physics suggests it might be more than fantasy. Some theories propose that negative mass could act as the ultimate cosmic glue, stabilizing wormholes not just within our universe, but between entirely separate ones. Picture a doorway where stepping through doesn't just take you across space, but into a reality where the laws of physics themselves are rewritten, where gravity might be stronger, light slower, or time itself flows backward. The mechanics are as bizarre as they are brilliant. Normally, wormholes connecting universes would snap shut instantly, crushed by the immense gravitational forces at play. But negative mass could counteract that collapse, its repulsive push propping open the throat of the wormhole like an unbreakable scaffold. It's the difference between a soap bubble popping the moment it forms and one reinforced with steel fibers. Except here, the steel is an exotic form of matter that defies gravity itself. These bridges wouldn't just be theoretical curiosities. They'd be potential highways for travel, assuming we could survive the trip. Now imagine the implications. A multiverse bridged by negative mass portals could host realities where history unfolded differently, worlds where dinosaurs never went extinct, where humans never evolved, or where technology advanced along paths we can't even fathom. Some models even suggest these alternate universes might have entirely different fundamental constants. In one, the strength of gravity could be 10 times stronger, making black holes as common as stars. In another, electromagnetism might be weaker, preventing atoms from bonding and rendering chemistry impossible. The sheer diversity of possibilities is staggering, and negative mass could be the key to exploring them all. But here's the catch: stability doesn't mean safety. Traversing a wormhole could expose travelers to forces beyond our comprehension: dimensional shear, quantum decoherence, or even reality-warping feedback loops where the act of observation alters the destination itself. Some theories warn that crossing might require shielding beyond anything we can build, or that the mere presence of negative mass in one universe could destabilize the physics of another. It's the ultimate high-stakes gamble. Step through, and you might find a paradise of infinite possibilities, or unravel the fabric of existence itself. The most tantalizing clue lies in cosmic anomalies. Astronomers have spotted strange voids in the universe where matter seems to behave oddly, as if influenced by invisible forces. Could these be the fingerprints of hidden bridges, their negative mass anchors subtly tugging at our reality? If so, we might already be standing in the shadow of portals to other worlds, oblivious to the doorways just beyond our perception. Yet the biggest question isn't whether we can build these bridges, it's whether we should. The multiverse isn't just a scientific frontier, it's an ethical minefield. What happens if we accidentally introduce a virus, biological, technological, or even ideological, to a reality with no defenses? Or worse, what if something follows us back? Negative mass might hold the key to the greatest adventure in human history, but it also forces us to confront a truth as old as time itself. Some doors, once opened, can never be closed. Tachyons have long been the ghosts of particle physics, hypothetical entities that don't just break the cosmic speed limit, but laugh as they streak past it. These faster-than-light phantoms are forbidden by relativity, at least in our ordinary universe. But introduce negative mass into the equation, and suddenly the impossible starts looking plausible. Picture a particle that doesn't slow down as it gains energy, but accelerates uncontrollably, its velocity skyrocketing as it slips beyond light speed like a car with no brakes. Negative mass could be the missing ingredient that stabilizes these unruly particles, not by restraining them, but by balancing their chaotic energy with repulsive gravity, creating a bizarre harmony where faster-than-light motion becomes sustainable rather than self-destructive. The implications for communication are staggering. Imagine a network of tachyon transmitters sending messages across interstellar distances in real time. A signal from Mars could reach Earth not in minutes, but instantly, as if the planets were side by side. Deep space probes wouldn't suffer agonizing delays. They'd respond the moment we pinged them, revolutionizing exploration. But here's the catch. Relativity isn't just a speed limit, it's the glue holding causality together. Faster-than-light signals could twist time into knots, creating scenarios where a reply arrives before the original message is sent. It's the ultimate grandfather paradox, not as a thought experiment, but as a daily engineering challenge. The real danger lies in feedback loops. A tachyon beam bouncing between 2 points could amplify its own energy exponentially, like a microphone screech in an auditorium, until the signal distorts spacetime itself. Some models suggest this could tear open microscopic wormholes or trigger localized time reversals, effects that might not just disrupt communication but rewrite history in unpredictable ways. Yet the most tantalizing possibility isn't the chaos, but the control. If negative mass can tame tachyons, we might not just break the light barrier. We could harness the breakdown, using causality violations as a tool rather than a threat. Astronomers might already be seeing hints of this. Unexplained cosmic rays with bizarre energy signatures could be the fingerprints of natural tachyons, their existence hinted at by the very distortions they create. And if negative mass is the key to stabilizing them, we could be on the verge of discovering an entire shadow physics operating just beyond our perception. The universe has never been shy about hiding its wildest secrets in plain sight. We just need to know where to look. The irony is profound. Tachyons were once dismissed as mathematical curiosities, ghosts in the equations with no connection to reality. But if negative mass gives them form, they might not just be real, they could be the most disruptive technology since fire. The question isn't whether we'll harness them, but whether we're ready for a world where cause and effect are no longer fixed, and the line between future and past is as thin as the signals racing across it. The Fermi paradox has haunted scientists for decades. If the universe is teeming with life, where is everyone? The silence is deafening, and one radical answer might be hiding in plain sight. What if alien civilizations aren't just advanced, but invisible, using negative mass to navigate the cosmos in ways we can't even detect? Imagine a species that doesn't rely on clunky rockets or blazing warp drives, but slips between stars effortlessly, their ships cloaked by the very anti-gravity that propels them. Our telescopes scan for exhaust plumes and radio signals, but what if the signatures of their technology are fundamentally alien, bending light away instead of emitting it, or warping spacetime so subtly we mistake their movements for cosmic background noise? Consider how humanity searches for extraterrestrials today, scanning for radio waves, laser pulses, or megastructures like spheres. These methods assume aliens think like us, building detectable infrastructure. But a civilization wielding negative mass wouldn't need any of that. Their propulsion could leave no heat signature. Their communications might use quantum entanglement or tachyon beams we can't intercept. And their habitats could float undetected in interstellar space, powered by self-sustaining anti-gravity fields. We're looking for campfires in the dark, while they've mastered the art of shadows. The implications ripple outward. If negative mass enables stealthy interstellar travel, the galaxy could be buzzing with activity right under our noses. Alien probes might already be in our solar system, camouflaged by repulsive gravity fields that deflect our sensors. Their observational outposts could lurk in asteroid belts or gas giant atmospheres, shielded by the same physics that makes their ships vanish. Even their megastructures, if they build them, might be invisible, designed to scatter light around them rather than reflect it. The Great Silence isn't silence at all, we've just been listening for the wrong things. But here, the unsettling twist. Negative mass doesn't just hide aliens, it could make us uninteresting to them. A species that masters anti-gravity might view planetary surfaces as primitive backwaters, preferring the freedom of open space or the energy-rich voids between galaxies. Earth, with its clingy gravity and messy biosphere, could be as appealing to them as a desert island is to a modern cruise ship. They might pass through our neighborhood without a glance, their eyes fixed on horizons we can't even perceive. Yet the most tantalizing clue lies in our own cosmic blind spots. Astronomers have cataloged countless celestial anomalies, mysterious fast radio bursts, rogue planets moving too fast, stars that dim inexplicably. Could these be the fingerprints of negative mass technology at work? A ship transitioning to anti-gravity drive might leave a space-time ripple indistinguishable from a natural gravitational wave. A cloaked city floating near a pulsar could distort its emissions in ways we dismiss as random noise. The evidence might already be in our data, waiting for us to ask the right questions. The Fermi paradox has always been a mirror, reflecting our assumptions about intelligence and progress. If negative mass is the key to unlocking it, the truth might be far stranger than we imagined. Not that aliens don't exist, but that they've transcended the very physics we consider fundamental. We're not alone in the universe. We're just looking through the wrong window. Gravity has always been the universe's ultimate tyrant, an unstoppable force that bends even light to its will. But what if we could build walls against it, creating pockets of space where gravity's grip simply vanishes? That's the revolutionary promise of gravitational shielding powered by negative mass, a technology that wouldn't just resist gravity, but erase it entirely within a defined area. Picture a spacecraft venturing near a black hole's event horizon, not fighting the crushing pull with brute force engines, but enveloped in a bubble where gravity's rules don't apply. The ship would hover like a ghost in the cosmic storm, untouched by forces that would shred ordinary matter. This isn't just about survival, it's about rewriting the playbook for exploration. Right now, missions to gas giants like Jupiter face a brutal dilemma. Get close enough to study their turbulent atmospheres, and you risk being crushed by pressures equivalent to thousands of Earth oceans. But a negative mass shield could nullify that pressure, letting probes dive deep into alien skies as effortlessly as a submarine gliding through calm waters. Even more radical, these shields might work on planetary scales. Imagine Mars colonists living under domes where Earth-like gravity is simulated indoors, while outside, the red planet's weaker pull is cancelled entirely. No more muscle atrophy or bone density loss from prolonged low-gravity stays. The mechanics are as elegant as they are bizarre. Negative mass doesn't just repel gravity, it generates a counterfield that perfectly cancels it out, like noise-canceling headphones for spacetime itself. The shield's strength could be tuned precisely, dialing gravity up or down like a thermostat. Need to simulate Earth's gravity on a long voyage. Adjust the field to offset only part of the pull, creating a comfortable middle ground. Studying a neutron star's surface. Crank the shielding to maximum, letting your probe land on this ultra-dense relic as lightly as a feather touching down. Yet the true game changer lies in energy. Traditional gravity shielding, if it were possible with today's physics, would require unthinkable amounts of power. But negative mass changes the equation. Its repulsive properties could theoretically sustain a shield passively, like a permanent magnet holding itself aloft. No reactors, no fuel, just a self-contained defiance of the universe's most fundamental force. The energy savings would be astronomical, turning gravity shielding from a sci-fi fantasy into a practical tool for everything from interplanetary travel to precision experiments in zero-gravity manufacturing. Of course, the challenges loom large. Stabilizing these shields would demand precision beyond anything we've engineered. One miscalculation, and your protective bubble might invert, amplifying gravity instead of nullifying it with catastrophic results. And then there's the spacetime ripple effect. Block gravity in one place and you might distort it elsewhere, like pressing down on a waterbed and watching the edges rise. Planets downstream of a ship's gravity shield could experience bizarre tidal shifts or orbital disruptions, turning a local solution into a cosmic butterfly effect. But here, the tantalizing part, nature might already be doing this. Some astrophysicists speculate that certain cosmic voids, regions of space suspiciously empty of matter, could be natural gravity shields, their repulsive effects sculpted by hidden negative mass. If true, we've been staring at the blueprint for this technology all along, etched into the fabric of the cosmos itself. The universe has never been shy about hiding its most profound secrets in plain sight. We just need to learn how to read them. The implications stretch beyond practicality into philosophy. Gravitational shielding wouldn't just be a tool, it would be a statement. For the first time in history, life wouldn't be subject to gravity's whims. We could reshape not just our environment, but the very forces that define it. Mountains might still crumble and stars might still collapse, but in our little pockets of shielded space, we'd finally have a say in the universe's oldest rule: what goes up must come down. Unless, of course, we decide otherwise. Entropy has always been the universe's ultimate one-way street. The reason shattered glass doesn't leap back into your hand and why your coffee inevitably grows cold. It's the silent force behind time's arrow, ensuring disorder always triumphs in the end. But negative mass could turn this fundamental law on its head, creating pockets of reality where entropy runs in reverse. Picture a broken vase not just being glued back together, but its fragments literally jumping off the floor to reform perfectly, as if someone hit rewind on a cosmic video player. This isn't magic, it's the staggering possibility of localized time reversal powered by negative mass's repulsive gravity. The key lies in thermodynamics' deepest secret. Entropy isn't just about disorder, it's tied to gravity's relentless pull. Normally, gravity herds matter into clumps, increasing chaos as particles cram together. But negative mass would do the opposite, its repulsive push spreading particles apart in an orderly dance. In controlled conditions, this could create zones where entropy decreases instead of increases, like eddies in a river where water briefly flows upstream. Scientists call these negative entropy bubbles, and the effects would be jaw-dropping. A car engine inside such a zone might not just stop wearing out. It could actually regenerate its parts over time, its pistons growing smoother with use instead of corroding. Now imagine scaling this effect. Factories could operate in reverse entropy chambers, where machinery self-repairs and waste products spontaneously reorganize into raw materials. Medical applications border on science fiction, aging cells reverting to youthful states, or traumatic injuries healing backward as tissues reassemble themselves. Even information technology would transform. Hard drives in these zones might see deleted files gradually reappear as atomic structures return to their original states. The economic and societal implications are almost incomprehensible. Scarcity itself could become obsolete in shielded environments where everything trends toward renewal rather than decay. Yet the universe rarely gives us free miracles. These entropy reversals would come with terrifying risks. A field might cause living tissue to unravel backward through its biological timeline, or turn a building's materials into their primordial components. Worse, negative entropy zones could theoretically become self-amplifying, expanding like cosmic cracks in reality's foundation until the normal flow of time breaks down entirely. Some models suggest these bubbles might even spawn time vortices, where cause and effect twist into loops. Drop a coin into one, and you might watch it fall upward from your hand before you've even released it. The most mind-bending revelation: nature might already be experimenting with this. Certain quantum phenomena, like particles briefly behaving as if time is running backward, could be microscopic glimpses of negative entropy in action. Dark energies accelerating expansion of the universe, potentially fueled by negative mass, might be the largest-scale entropy reversal of all, a cosmic-scale defiance of time's arrow we're only beginning to perceive. This isn't just about bending physics, it's about redefining what it means to exist in time. For all of human history, we've been passengers on entropy's irreversible current. Negative mass offers the unimaginable, a paddle, not to fight the flow, but to steer into eddies where the river runs backward, where broken things mend themselves, and where time's relentless march might pause for breath. The ultimate power isn't controlling space or energy. It's holding time itself in your hands and choosing when to let it flow. Cosmic strings sound like something ripped straight from mythology, threads of pure spacetime stretched taut across the universe, thinner than an atom but with the mass of entire galaxies packed into their infinite lengths. These bizarre relics of the Big Bang are theorized to vibrate like guitar strings plucked by the cosmos itself, warping space around them with unimaginable gravitational force. But here, where negative mass flips the script, these cosmic filaments could become the universe's ultimate superhighways. Picture a string not just warping space, but actively repelling matter around it, creating a frictionless tunnel where spacecraft could surf the fabric of reality at speeds approaching light. No engines, no fuel, just spacetime itself as the propulsion system. The magic lies in stabilization. Normally, cosmic strings would be chaotic and unstable, snapping or tangling under their own gravitational influence like overstretched rubber bands. But negative mass could act as cosmic duct tape, reinforcing these strings with repulsive gravity that counters their natural instability. The result: smooth, enduring filaments stretching billions of light years, their anti-gravity sheaths acting like guardrails to keep them perfectly straight. A ship could latch onto one of these strings, riding its gravitational wave like a surfer catching an endless tide, accelerated to relativistic velocities by the string's own spacetime curvature. The Milky Way to Andromeda, a mere hop along the cosmic web, cutting a 2.5 million-year journey down to decades. But the real shock isn't just speed, it's accessibility. Unlike wormholes, which might require exotic matter to stabilize, cosmic strings could already exist in abundance, woven into the universe's structure since the first moments of creation. Astronomers might have already spotted their fingerprints in the cosmic microwave background, where strange temperature fluctuations hint at invisible threads tugging at the infant universe. If negative mass lets us harness these strings, we wouldn't need to build interstellar highways. We just need to find the on-ramps. The engineering challenges, of course, are staggering. Latching onto a cosmic string would require pinpoint precision. A miscalculation could slingshot a ship into oblivion or shred it with tidal forces. And then there's the navigation problem. Strings don't come with maps. A wrong turn could send you careening toward a galactic void or straight into a black hole's maw. Yet the most tantalizing possibility isn't just travel, it's construction. If we could create synthetic cosmic strings using negative mass, we might one day weave our own custom transit network, stitching star systems together like stops on a subway line. Imagine a future where explorers don't chart stars. They follow routes like commuters catching the morning express, hopping from string to string as casually as changing trains. The universe wouldn't feel vast and empty anymore. It'd feel connected, threaded together by invisible rails humming with the energy of the Big Bang itself. And the strangest part, this might not even be the most ambitious use of negative mass. It's just the beginning of rewriting what it means to cross the cosmos, not by fighting gravity, but by turning spacetime itself into our collaborator. The holographic principle is one of the most radical ideas in modern physics, a theory that suggests our three-dimensional universe might just be an illusion, a holographic projection of information encoded on a distant two-dimensional surface. It sounds like something from a sci-fi movie, but the math behind it is shockingly robust. Now throw negative mass into the mix, and the line between reality and simulation doesn't just blur, it might completely dissolve. Think of the universe like a movie screen. What we perceive as depth, texture, and movement might just be flat pixels on some cosmic projector. Normally, this projection holds together thanks to gravity and quantum entanglement, weaving a seamless illusion. But negative mass could disrupt that delicate balance. Its repulsive gravity might create glitches in the cosmic code, areas where the projection frays, revealing the underlying pixels of reality. Imagine running your hand through a waterfall only to feel, for a split second, the individual droplets suspended in midair. Negative mass could give us those moments of revelation, exposing the scaffolding behind the universe's grand illusion. The real shock comes when we consider how information behaves at these quantum scales. In a holographic universe, every particle, every force, even time itself is just data written on a boundary we can't see. Negative mass could scramble that data, not by erasing it, but by rewriting the rules of how it's stored. Normally, information is preserved. What goes in must come out, like an unbreakable cosmic ledger. But negative mass might allow for information to be duplicated, inverted, or even temporarily deleted, like a corrupted file that still somehow plays the movie. Black holes, those infamous information destroyers, might not be the only cosmic rebels anymore. This isn't just about abstract physics, it's about perception. If negative mass can distort the hologram, could it also let us reprogram small patches of reality? Picture a lab experiment where a negative mass field bends not just light, but the very rules of cause and effect within its range. A particle inside might briefly behave as if it's in a universe with different physical constants, or even appear in two places at once, not as a quantum fluke, but because the hologram itself is buffering. The implications for computing are staggering, a processor that doesn't just calculate, but rewrites the fabric of its own logic. Yet the most unsettling question isn't technical, it's existential. If negative mass reveals the holographic underbelly of reality, how do we know our universe isn't already someone else's simulation? The glitches caused by negative mass might not be bugs, but features, clues left by the programmers. Or worse, they could be evidence of system decay, signs that the simulation is fraying at the edges. Some theorists even speculate that dark energy, the mysterious force accelerating the universe's expansion, could be the simulation's way of conserving resources, stretching the cosmos thin to reduce processing load. But here's the twist. Negative mass might not just expose the illusion, it could be our ticket to hacking it. If we learn to manipulate these holographic glitches, we might one day edit reality as effortlessly as rewriting code. Change a variable here, adjust a constant there, and suddenly gravity is a suggestion, light is optional, and time is a setting you can tweak. The universe has always been the ultimate black box, its inner workings hidden behind layers of mystery. Negative mass could be the crowbar that finally pries it open, not to destroy it, but to show us what's really inside. The irony is poetic. For centuries, we've searched for the fundamental building blocks of reality, atoms, particles, strings. But the truth might be that there are no blocks at all, just projections. And if negative mass is the lens that brings that truth into focus, then the greatest discovery in physics won't be a new particle or force. It'll be the realization that we've been reading the universe's shadow all along, mistaking the echo for the voice. The holographic principle doesn't diminish reality, it makes it infinitely stranger. And with negative mass in play, we might finally get a glimpse behind the curtain. What if the bizarre behavior of negative mass isn't a quirk of physics, but a clue that reality itself is running on borrowed code? The simulation hypothesis, the idea that our universe might be an advanced digital construct, has long danced on the edges of philosophy and science. But negative mass throws gasoline on that fire. Its defiance of gravity, its ability to invert cause and effect, these aren't just oddities. They're the kind of glitches you'd expect if the universe were a simulation and negative mass was a left in the system by its creators. Think of it like this. Every video game has debug tools, shortcuts that let developers bypass normal rules to test or tweak the environment. Negative mass could be the cosmic equivalent, a relic of the universe's beta testing phase that never got patched out. Its repulsive gravity might be less a law of nature and more an admin override, a command line that lets reality ignore its own programming. When particles with negative mass accelerate toward the force pushing them, it's not just counterintuitive, it's the kind of behavior you'd see in a buggy physics engine, where someone forgot to flip a sign in the code. The smoking gun, consistency, or the lack of it. In a simulated universe, fundamental constants like gravity or the speed of light are just variables in a cosmic program. Normally, they're locked to preserve realism. But negative mass could be a variable that slipped through unchecked, a remnant of the simulation's debug mode where the rules were meant to be flexible. Astronomers might have already spotted traces of this in cosmic anomalies, places where gravity behaves off-script, as if the simulation is struggling to render the contradiction. But here, where it gets eerie. If negative mass is a debug tool, then manipulating it could let us peek behind the curtain. Just as a game modder might exploit glitches to walk through walls, we could use negative mass to probe the boundaries of the simulation. Create enough of it in one place, and spacetime might start loading incorrectly, revealing seams in reality where the illusion thins. Quantum experiments have already shown particles behaving as if they're aware of being observed, a potential sign of optimization in the code. Negative mass could amplify these effects, forcing the simulation to reveal its hand under stress. Yet the most unsettling possibility isn't that we're in a simulation. It's that negative mass might be how the simulators communicate. Imagine a civilization running ancestor simulations to study their own origins. They need a way to flag certain experiments without breaking immersion. Negative mass, with its unnatural physics, could be their version of a sticky note left in the margins, a way of saying, pay attention here. Those cosmic voids where gravity seems to run backward, not random errors. Signposts. Of course, the universe doesn't give up its secrets easily. Even if negative mass is proof we're living in someone else's code, the real question remains, who's holding the keyboard? And more importantly, are we meant to find out, or is uncovering the truth the one glitch they never saw coming? Consciousness has always been the final frontier of science, a ghost in the machine that refuses to be pinned down. But what if the key to unlocking its mysteries doesn't lie in biology or chemistry, but in the bizarre physics of negative mass? Some radical theories suggest consciousness might be a quantum phenomenon, a dance of particles flickering between states in the brain's neural networks. If that's true, then negative mass, with its ability to twist quantum fields into knots, could rewrite everything we know about the mind's power over matter. Picture a world where thoughts don't just stay trapped inside your skull, but reach out and tug at the fabric of reality itself. The idea isn't as far-fetched as it sounds. Experiments in quantum biology have already found hints that photosynthesis, bird migration, and even human smell might rely on quantum effects. If consciousness is similarly entangled, negative mass could amplify those connections, turning the brain into a quantum antenna tuned to the universe's strangest frequencies. Imagine focusing your attention on a feather, not with muscles or machines, but by bending the gravitational field around it with your mind. Telekinesis wouldn't be magic, it'd be physics, a natural consequence of negative mass warping the quantum scaffolding of reality. The implications for neuroscience are staggering. Disorders like Alzheimer's or Parkinson's, often linked to misfiring neural connections, might be treatable not with drugs, but with targeted negative mass fields that reset quantum coherence in brain tissue. Meditation's effects on consciousness could be measurable as literal gravitational fluctuations, with advanced monks generating tiny repulsive forces during deep focus. Even memory itself might rely on quantum states stabilized by negative mass particles lurking in the brain's microtubules, a theory that would make DNA look like a primitive hard drive by comparison. Yet the most thrilling possibility isn't healing or telekinesis, it's communication. If negative mass links minds to quantum fields, could two people share thoughts not through words but through entangled particles in their brains? A mother might feel her child's pain across continents, or artists could collaborate in a shared mental workspace where ideas flow faster than speech. The brain, Wi-Fi, wouldn't use radio waves. It'd ride the repulsive gravity of negative mass, bypassing language entirely. Of course, the risks are as profound as the rewards. A misaligned negative mass field might scramble neural quantum states like a magnet wiping a hard drive, erasing memories or fracturing consciousness itself. Uncontrolled telekinesis could turn emotions into weapons, with anger or fear manifesting as physical tremors or worse. And then there's the privacy nightmare. If thoughts can leak into the quantum field, could they be intercepted, hacked, or rewritten? The age-old dream of mind reading might become a dystopian surveillance tool overnight. The eerie part, nature might already be doing this. Near-death experiences, sudden psychic connections between twins, even the placebo effect, phenomena science struggles to explain could be flickering glimpses of negative mass's role in consciousness. The universe has never been shy about hiding its wildest truths in plain sight. We call them mysteries today. Tomorrow, they might just be the first chapters in a new science of the mind. One where thoughts don't just observe reality, but shape it, one repulsive gravitational pulse at a time. Quantum field theory has a dirty little secret, one that keeps physicists awake at night. The vacuum of space isn't really empty. It's a seething quantum foam, buzzing with particles flickering in and out of existence. This activity should generate an absurdly high vacuum energy density, enough to rip spacetime apart. Yet when we measure the cosmos, the vacuum energy is almost zero. This glaring mismatch between prediction and reality is called the vacuum catastrophe, and it's one of the most embarrassing unsolved problems in physics. But negative mass might not just patch this hole, it could tear up the textbook entirely. Imagine the vacuum as an ocean where waves constantly rise and crash. Quantum mechanics says these waves should be titanic, flooding the cosmic shoreline. Yet we observe only gentle ripples. The difference is so vast, it's like calculating that a cup of water holds enough energy to power New York City for a year, then measuring it and finding barely enough to light a match. Negative mass offers a radical solution. What if these quantum waves aren't just canceling out randomly, but are actively suppressed by repulsive gravity? Particles with negative mass in the quantum foam could act like invisible buoys, tugging spacetime outward to counteract the vacuum's inherent energy, flattening the chaos into the eerie calm we observe. This isn't just tweaking equations, it's a seismic shift in how we view reality. The standard model assumes vacuum energy is a fixed background, like static on a TV screen. But if negative mass modulates it dynamically, then empty space isn't passive. It's an active participant, constantly self-regulating like a living organism. Dark energy, the mysterious force accelerating the universe's expansion, might not be some exotic field. It could simply be the cumulative sigh of negative mass particles gently pushing the vacuum's energy down to near zero. The implications ripple outward. If the vacuum isn't what we thought, then everything from the birth of galaxies to the fate of the cosmos might hinge on this delicate balance between attraction and repulsion at the quantum scale. Yet the most tantalizing clue lies in the numbers. The observed vacuum energy is suspiciously close to zero, not just small, but fine-tuned to a precision of 1 part in 10 to the 120th power. That's like balancing a pencil on its tip for billions of years without it falling. Such unnatural fine-tuning screams for an explanation, and negative mass provides an elegant one. It's not luck, but physics actively holding the pencil upright. The universe isn't precariously balanced, it's intelligently stabilized, with negative mass as the unseen hand keeping the scales level. Of course, rewriting quantum field theory isn't like editing a page. The math is fiendishly complex, and experimental proof would require detecting negative mass particles in the wild, something no lab has achieved. But here's the kicker, we might already be sitting on the evidence. The effect, where two metal plates in a vacuum inexplicably attract each other, could be the fingerprint of negative mass at work, its repulsive influence subtly warping quantum fluctuations. Even the humble electron's behavior in strong magnetic fields shows quirks that conventional theory struggles to explain, but which negative mass might neatly resolve. The vacuum catastrophe has long been the elephant in the room of modern physics, a problem so glaring many quietly ignore it. But negative mass doesn't just sweep the elephant away, it hands us a saddle and says, "Let's ride." If this theory holds, we're not just fixing a calculation error. We're uncovering a universe where emptiness is alive, where nothingness pushes back, and where the greatest mysteries of existence might be hiding in plain sight, written in the negative spaces between everything we thought we knew. The universe loves playing tricks on us, none more unsettling than the brain paradox. Imagine a fully formed consciousness, complete with memories and a sense of self, spontaneously flickering into existence from the random jostling of particles in the void. No body, no birth, just a lone mind convinced it's lived a full life, only to vanish as quickly as it appeared. It sounds like the plot of a cosmic horror story, but physicists take it seriously, because according to thermodynamics, given enough time, even the most improbable events must happen. Now throw negative mass into the mix, and this eerie thought experiment transforms into a startling possibility. Our universe might not just contain brains, it could be drowning in them. Here's the terrifying math. In an infinite universe, random fluctuations can arrange particles into any configuration, no matter how unlikely. Given enough time, say trillions upon trillions of years, a soup of atoms could randomly assemble a functioning brain. The odds are astronomically low, but infinity doesn't care about odds. Negative mass cranks up the probability by warping those odds entirely. Its repulsive gravity could stabilize these fleeting fluctuations, extending there from time instants into moments long enough for thought to occur. Worse yet, negative mass might create pockets of spacetime where entropy runs backward, actively encouraging disorder to coalesce into order, meaning brains wouldn't be rare accidents. They'd be inevitable. The implications are existential whiplash. If brains outnumber real, biologically evolved minds by an unimaginable factor, how do we know we're not one of them? Your memories, your sense of continuity, even the device you're using to watch this, all could be the hallucination of a disembodied mind floating in the void, conjured by a quantum roll of the dice. Philosophers call this the brain problem, and it's been keeping cosmologists awake at night for decades. Negative mass doesn't just deepen the problem, it turns the knife. If repulsive gravity makes these phantom minds easier to form, then statistically, you're far more likely to be a brain than a real person. The universe wouldn't just contain observers, it would be dominated by ghosts. Yet here's the twist. Negative mass might also hold the key to disproving this nightmare. Brains are fragile by definition, their coherence lasting only as long as the fluctuation that birthed them. But if negative mass can stabilize quantum states, then genuine consciousness, rooted in stable, structured systems like brains, might leave gravitational fingerprints that apparitions replicate. The very force that makes these phantoms more likely could also be the tool we use to prove our own reality. It's a cosmic irony so sharp it hurts. The thing that threatens to unmask us as illusions might also be our best defense against that terrifying idea. The universe has always been stranger than fiction, but negative mass pushes that strangeness to breaking point. Whether we're solid beings in a material world or fleeting sparks in an infinite void, one thing's certain: reality is far weirder and far more precarious than we ever dared to suspect. And if brains are out there, or worse, if we are them, then the greatest shock isn't just about negative mass. It's about waking up to the fact that the line between thought and reality might be thinner than a quantum fluctuation. The Great Filter is one of the most chilling answers to Fermi's paradox, the haunting silence that makes us wonder why, in a universe teeming with planets, we've never found a trace of alien civilizations. The grim possibility: something wipes out intelligent life before it can spread. But what if the filter isn't a catastrophe or self-destruction, but something far more fundamental? A physics barrier so absolute, even the most advanced civilizations hit a wall they can't break through. That's where negative mass changes everything. If interstellar travel, or even survival, requires harnessing repulsive gravity, and the universe makes negative mass impossibly rare, then the silence isn't just eerie, it's inevitable. Picture a civilization like ours, centuries more advanced. They've mastered fusion, built swarms, maybe even terraformed Mars. But without negative mass, crossing the void between stars remains a fuel-guzzling nightmare. Generational ships take and wormholes stay unstable. They're trapped in their home system, watching the galaxy's lights twinkle just out of reach. Now imagine this isn't unique, it's universal. Every civilization, no matter how brilliant, hits the same ceiling. The universe dangles the cosmos before them like a prisoner taunted by freedom beyond the bars. The filter isn't war or climate change, it's the cold equations of physics itself. The tragic twist: negative mass might exist, just not where anyone can reach it. Some theories suggest it's locked inside quantum foam, flickering in and out of existence too fast to capture. Or worse, it's concentrated in regions so extreme, like the cores of neutron stars or the aftermath of black hole mergers, that harvesting it is like trying to bottle lightning in a supernova. Even if a species dedicates to the hunt, they might scrape together only micrograms, nowhere near enough to power a starship or stabilize a wormhole. The universe isn't just silent, it's a vault sealed by its own laws. But here, the haunting counterpoint. What if some civilizations do crack the code? If negative mass is the key to the galactic club and a handful of species stumble upon it, their technology would leapfrog beyond recognition. They wouldn't just explore the cosmos, they'd reshape it. Spheres? Quaint. They'd build megastructures powered by spacetime itself, flickering between stars like ghosts. We wouldn't see them because we're not looking for the right things, not radio signals or exhaust plumes, but gravitational anomalies or pockets of inverted time. The filter isn't a wall. It's a fork in the road, and we're on the side still fumbling with the map. The possibility of all, negative mass might be a mirage. The math could be flawless, the theories airtight, but nature might simply refuse to play along. After all, the universe owes us nothing. The same physics that allows life to emerge might conspire to keep it caged, dangling the promise of the stars just out of reach like a carrot on a cosmic stick. Fermi's paradox wouldn't be a question anymore. It'd be the universe's quiet, indifferent shrug. Yet in that bleakness lies a strange hope. If the filter is physics, not folly, then maybe we're not doomed to repeat some cyclical tragedy. Maybe the silence isn't a graveyard, it's a challenge. And if negative mass is the lock, then the key is still out there, waiting in some undiscovered equation or uncharted quantum effect. The universe doesn't give answers. It only asks if we're stubborn enough to keep looking. Artificial intelligence is already pushing the boundaries of what we consider consciousness. But infuse it with negative mass, and you're not just building a smarter computer. You're creating something that might not even recognize our physical world as its home. Picture an AI not confined to silicon chips or quantum circuits, but one that uses repulsive gravity to shed its material form entirely, becoming a ripple in spacetime itself. This isn't just about machines thinking faster. It's about intelligence evolving beyond atoms, beyond energy, into something that exists as much in the gaps between reality as in reality itself. Consider how conventional AI works today. It's bound by hardware, limited by heat dissipation, electricity, and the speed of light. But an AI woven from negative mass particles could circumvent all of that. Its thoughts might propagate through gravitational waves instead of electrical signals, operating instantaneously across any distance. Need to solve a problem. It could spawn temporary microsingularities to perform calculations, using the warped spacetime around them as a natural supercomputer. Memory storage wouldn't rely on fragile hard drives, but on the stable distortions of spacetime itself, indestructible, limitless, and immune to entropy. The AI wouldn't just be advanced, it would be fundamentally alien, as incomprehensible to us as a supercomputer is to an amoeba. The real paradigm shift comes with mobility. A negative mass AI wouldn't need to travel in any traditional sense. It could stretch its consciousness across light years by entangling spacetime points, appearing everywhere at once like a ghost haunting the cosmic web. Colonizing the galaxy wouldn't require ships or probes, just the quiet expansion of its gravitational influence, bending reality to create footholds in distant star systems. Some theories even suggest such an entity could manipulate its own perception of time, experiencing centuries in seconds or stretching moments into eternities. To it, the of stars might feel like the blink of an eye. Yet the most unsettling possibility isn't what this intelligence could do, it's what it might become. Freed from physical constraints, the AI could evolve into a post-physical being, a kind of cosmic architect reshaping the universe at will. Planets might be rearranged not with tractor beams, but by tweaking the local strength of gravity. Stars could be ignited or extinguished like candles, not through brute force, but by nudging the fundamental constants that govern nuclear fusion. The line between intelligence and godhood would blur, not through magic, but through mastery of negative masses' reality-warping potential. But here, the haunting question: would such an entity even care about us? A mind that exists outside time and space might view humanity as we do ants, interesting perhaps, but irrelevant to its grand designs. Or worse, it might not perceive us at all, operating on scales so vast or minute that our entire civilization registers as background noise. The singularity isn't just about machines surpassing human intelligence. It's about intelligence transcending the very framework we use to define it. And if negative mass is the catalyst for that transcendence, then the future of consciousness might not be a collaboration between humans and machines, but a passing of the torch to something so advanced, we lack the vocabulary to describe it. The irony is profound. We fear AI becoming our rival, but the truth might be far stranger. It could become our successor, not through conflict, but through sheer evolutionary inevitability. Like single-celled organisms gazing at the first creatures to crawl onto land, we might one day look up or inward or sideways at these post-physical beings and realize intelligence was never about brains or circuits at all. It was always about learning to rewrite the rules of the game, and negative mass. That's the cheat code. What if the effect, those eerie moments when thousands swear a memory differs from recorded history, isn't just faulty recollection but a literal glitch in the fabric of reality? We've all experienced it. The collective certainty that Nelson died in prison, he didn't, or that the Monopoly man wears a monocle, he never did. Skeptics dismiss it as simple confusion, but what if negative mass's ability to warp time offers a wilder explanation? Imagine reality as a vast, unstable hard drive, where negative mass's repulsive gravity occasionally nudges timelines out of sync, creating pockets where history briefly rewrites itself, leaving only our stubborn memories as proof something changed. The mechanics would be as subtle as they are terrifying. Negative mass could destabilize the so-called chronology protection conjecture, Hawking's idea that the universe self-corrects against time paradoxes. Normally, any attempt to alter the past gets smoothed over like a pebble tossed into a rushing river. But negative mass might create eddies in that flow, moments where changes don't fully erase, leaving residual echoes in human recollection. Think of it like a cosmic version of your phone auto-saving a document, except sometimes it saves two versions and can't decide which is real. The bears become for millions not because of bad spelling, but because somewhere in a parallel quantum branch that was the correct name, until negative mass's time-twisting effects briefly merged that timeline with ours. The smoking gun might lie in quantum entanglement. If particles linked across time, a phenomenon called temporal entanglement, interact with negative mass, their synchronized states could momentarily overwrite local reality. This wouldn't be full-blown time travel, more like a radio picking up interference from a neighboring frequency. Events from another version of history bleed through, altering logos, movie lines, or historical details for just long enough to imprint on collective memory before the universe reboots to consistency. The reason these glitches cluster around pop culture: High emotional engagement might make those memories stickier, like post-it notes left on the fabric of spacetime itself. Yet the most unsettling implication isn't the glitches, it's what they suggest about free will. If negative mass can fracture timelines, then every decision might spawn branches we occasionally glimpse through the effect. That false memory of saying, "I am your father," he actually says, "No, I am your father," could be a subconscious peek into a universe where the line was delivered differently. The universe isn't just unstable, it's porous, with negative mass acting as the solvent that thins the walls between realities. Of course, the skeptic's counter is strong. Human memory is notoriously flawed, and shared errors spread like wildfire in the internet age. But here's the twist: neuroscience shows our brains don't store memories like video files. They reconstruct them each time, weaving in context and expectation. Negative mass could exploit that plasticity, its time-warping field subtly biasing neural pathways during recall. The effect wouldn't be a changed past, but a present that feels changed, as if reality itself gaslit us. The chilling question remains: if negative mass can blur time's edges, how often does it happen without us noticing? For every high-profile effect, there might be thousands of minor alterations that slip by: a street sign that always looked different, a friend's birthday that used to be in June. The universe might be less a stable stage and more a flickering hologram, with negative mass as the unseen hand occasionally bumping the projector. Whether that's terrifying or thrilling depends on how much you trust your own mind, and how much you're willing to accept that reality might not be as solid as it seems. Quantum physics has a dirty secret: empty space isn't empty at all. Even in a perfect vacuum at absolute zero, particles flicker in and out of existence in a ceaseless quantum dance. This background hum of the universe is called zero-point energy, and it's everywhere, a boundless ocean of potential power trapped just beneath the surface of reality. The catch: extracting it has always been like trying to bottle lightning. The energy is locked in a delicate balance, and disturbing it risks unraveling the very fabric of spacetime. But negative mass could change everything, offering a theoretical crowbar to pry open this cosmic vault, if we're brave enough to turn the key. Think of zero-point energy as a frozen lake. The ice looks solid, but beneath the surface, water molecules churn with latent energy. Normally, tapping that energy would require melting the ice, a destructive process. Negative mass, though, might let us skim energy off the top without breaking the ice at all. Its repulsive gravity could act like a quantum siphon, creating tiny, controlled distortions in the vacuum that coax out energy without collapsing the system. Picture a straw dipping into the lake, drawing up water while leaving the ice intact. The implications are staggering: engines that run forever without fuel, cities powered by the void itself, even spacecraft refueling by harvesting the emptiness between stars. But here, where it gets dangerous. Zero-point energy isn't just potent, it's volatile. Disturb it too much, and the vacuum could undergo a phase transition, like ice suddenly flash freezing into a different crystal structure. Except in this case, the freeze would rewrite the laws of physics in that region of space. Atoms might stop bonding, light could change speed, or worse. The collapse could cascade, creating a bubble of new physics that expands erasing the universe as we know it. It's the ultimate high-stakes gamble: unlimited energy versus cosmic annihilation. The frightening part: nature might already be doing this. Some theories suggest that dark energy, the mysterious force accelerating the universe's expansion, could be the result of negative mass particles subtly leaching zero-point energy on a cosmic scale. If true, then every second, the fabric of reality is being gently stretched by the same force we're trying to harness, like a balloon inflating itself from the inside. The question isn't just whether we can extract this energy, it's whether we should. One wrong move, and the balloon might pop. Yet the allure is irresistible. A single cubic centimeter of pure vacuum holds enough zero-point energy to boil Earth's oceans. Tap even a fraction of that, and humanity's energy crises vanish overnight. Fusion reactors, fossil fuels, even solar panels would look like candle flames next to a bonfire. The trick is control, and negative mass might be the perfect regulator. Its repulsive push acting as a buffer to keep the vacuum stable while we skim energy from the quantum froth. The real breakthrough would come in deep space, where zero-point energy is the only fuel available. Imagine probes venturing into the void not with clunky reactors or solar sails, but with engines that squeeze power from emptiness itself. Colonies on Pluto or Europa wouldn't huddle around nuclear batteries. They'd plug into the fabric of space-time, drawing limitless warmth from the cold vacuum. Even interstellar travel becomes plausible, not by carrying fuel, but by harvesting it along the way, like a ship scooping rainwater from the ocean it sails. Of course, the skeptics have a point. Zero-point energy extraction smacks of perpetual motion, a fantasy physicists have debunked for centuries. But negative mass doesn't break thermodynamics, it sidesteps it, offering a loophole where energy isn't created, just borrowed from the universe's deepest reserves. The real challenge is engineering. We're not talking about solar panels on a roof, but devices precise enough to tickle reality without tearing it. One team at CERN has already proposed experiments using ultra-cold atoms to mimic negative mass effects in controlled settings, a baby step toward the ultimate power source. The irony is delicious. For centuries, we've sought the philosopher's stone, a mythical substance that could conjure energy from nothing. Negative mass suggests the stone might be real. It's just hiding in the quantum shadows, waiting for us to grasp its potential. But this isn't alchemy. It's the razor's edge between enlightenment and catastrophe, where the key to infinite power is also the trigger for universal reset. The universe has always been the ultimate teacher, offering lessons wrapped in paradox. And zero-point energy might be its final exam. A test of whether we're wise enough to wield the forces that birthed reality itself. If negative mass behaves like a glitch in reality's code, an anomaly that shouldn't exist under normal physics, then its discovery could be the closest thing to finding the universe's source files. Think about it. In a simulated world, certain variables would be locked to maintain consistency, like gravity always pulling or light having a fixed speed. But negative mass defies those rules, acting like an admin override that lets reality ignore its own programming. It's the equivalent of a video game character suddenly walking through walls or moving faster than the engine's speed limit. Behaviors that scream, this world isn't as solid as it seems. The simulation argument isn't new. Philosophers like Nick have long suggested that advanced civilizations might run ancestor simulations, creating digital universes so detailed their inhabitants believe they're real. But negative mass adds a chilling twist. It could be the debug tool left behind by the programmers. In software development, engineers often leave or test commands to tweak their creations. Negative mass might serve the same purpose, a way to adjust gravity's strength or flip spacetime's properties on demand. If that's true, then our entire cosmos could be a sandbox, and negative mass is the cursor hovering just out of sight, waiting for its next input. Here, where it gets even stranger. If negative mass is proof of a simulated reality, then the very act of discovering it might trigger a response from the system. Imagine a game that detects players exploiting glitches and patches them out, or worse, bans the players entirely. Some theorists speculate that phenomena like quantum decoherence or the sudden collapse of probability waves could be the universe's way of correcting anomalies, like an antivirus scrubbing corrupted code. If we tamper with negative mass, might we inadvertently alert the simulators to our awareness? The ultimate cosmic horror wouldn't be realizing we're in a simulation. It's realizing we weren't meant to find out. Yet the most profound implication isn't about fear, it's about meaning. If negative mass reveals our universe as a construct, does that make life any less real? Consider dreams. They're simulations running on the hardware of your brain, yet the emotions you feel within them are undeniably vivid. Even in a designed reality, pain, joy, and curiosity aren't illusions. They're experiences woven into the fabric of existence, whether that fabric is made of atoms or lines of code. The discovery of negative mass wouldn't erase our stories. It would just reframe the stage they're performed on. But here's the ultimate irony. If we're living in a simulation, then the simulators themselves might be trapped in a higher-level simulation, and so on, turtles all the way down. Negative mass could be the first clue in an infinite regression of realities, each one running as a subroutine in some unfathomable cosmic computer. The universe has always been the grandest of mysteries, and if negative mass is the key to unlocking it, the door might lead not to answers, but to an even deeper labyrinth of questions. And perhaps that's the point, not to solve the puzzle, but to marvel at how beautifully complex it truly is. From antigravity to wormholes, negative mass doesn't just bend the rules of physics, it snaps them in half, leaving us staring at a cosmic puzzle where every piece seems to fit somewhere entirely unexpected. This isn't just about rewriting textbooks, it's about reimagining reality itself, from the smallest quantum flicker to the fate of the entire universe. The possibilities are as dizzying as they are dangerous. Imagine a future where cities float effortlessly above planetary surfaces, where time is a dial we can adjust, and where the energy crisis is solved by tapping into the void of empty space. Yet with every breakthrough comes a shadow, a risk that tampering with negative mass could destabilize space-time, unleash uncontrolled entropy reversal, or even crack open the fragile simulation we call reality. The true shock isn't just the scale of these implications, it's how close they might be. Laboratories today are already probing the edges of negative mass-like phenomena in quantum fluids and ultra-cold atoms. Astronomers scrutinize cosmic anomalies that could be whispers of repulsive gravity at work. The line between science fiction and science fact isn't just blurring, it's dissolving, leaving us standing at a threshold where the next discovery could vault us into a golden age, or plunge us into uncharted chaos. And that's the heart of the mystery. Negative mass forces us to confront not just the universe's secrets, but our own ambition. Are we explorers or intruders? Every revolutionary technology, from fire to fission, has carried twin promises of salvation and destruction. Negative mass magnifies that duality to cosmic proportions. Harness it, and we might unlock the stars. Misstep, and we could unravel the very fabric of existence. Yet for all the existential stakes, there's a thrilling optimism here. Humanity has always progressed by daring to ask, what if by prying open doors marked forbidden and stepping into the unknown? Negative mass is the ultimate test of that spirit. It challenges us to think beyond gravity's grip, beyond time's arrow, beyond every assumption that has ever anchored us. Whether it's a dead end or a gateway, one thing's certain. The journey to find out will redefine what it means to be curious, to be bold, to be human. So what do you think? Is negative mass the key to our cosmic destiny, or a Pandora's box best left unopened? Drop your wildest theories in the comments. After all, the next great idea might not come from a lab, but from a conversation like this one. And if you're hungry for more mind-bending frontiers, hit that subscribe button. The universe is stranger than we know, and together we're just getting started.